Exercise 5I, modeling. Today we are learning about solving application problems. What you need to be able to do is break down worded problems into equations, draw a flow chart to explain what you need to do to solve the problem, find the unknown, and write a worded answer. So we're up to the end of the chapter for exponentials and logs. And of course, with maths, we want to try and apply it to real life. So my question to you is, where would we find exponentials in real life? Take a moment to pause the video and maybe try to write down a list of where you might. So some places that you would find it and some common questions that you'll come across are things like population growth. COVID's a really popular one. If you remember the news, it was like one person had it, then two people, and then suddenly eight people, and then 30 and hundreds. It just absolutely blew up. Uh, on the opposite direction, so decaying, we have something called radioactive decay. So there are certain elements in the earth that will decay over time. So they'll decay rapidly at first and then they'll slow down, or the other way around. And of course, just general things like heating and cooling. So when you are heating up a room, it'll heat up quite quickly, but then it'll stabilize at some point, and same with cooling. So the idea of exponential and logarithmic modeling is that functions can be used to model real life situation. These models can then be used to make predictions. In most cases, when modeling real life situation, the domain is going to be restricted from 0 to infinity because time will not be negative. So generally, we will start at 0. All right, let's go for it and try a few of these questions. So, example 22. Manoj pours himself a mug of coffee, but gets distracted by a phone call before he can drink the coffee. The temperature of cooling of the mug of the coffee is given by this particular equation, where T is the temperature of the coffee and little t is the minutes after it was initially poured into the mug. What was its initial temperature? So, notice that I'm kind of highlighting as I go along as well. Initial is a key word here. Initial is when time has started. So that would be always at t is equal to 0, little t. So we will substitute that in. Now, of course, you would be expected to just use your CAS calculator. Just for speed's sake, I might just give you the answer to some of these questions. In this case, you can actually do this one in your head because this is just to the power of 0, and we know anything to the power of 0 is 1. So that'll just be 20 plus 75, which is 95 degrees. Next question says, to what temperature will the coffee cool if left unattended? So what we're thinking about if left unattended means that over a long time. So over a long time or in the long run is the specific language that you'll see being used in the long run. This always refers to what happens in the long run, which is the asymptote. So you need to recognize the language where they're asking about what is the asymptote of this equation. Now, if you think about your exponential equation, you know that these are just dilation factors, and that what's happened here is that our whole function has been lifted up by 20. So our asymptote is at y is equal to 20. Therefore, over time, if left unattended, I think I spelled that weird. Unattended, the coffee will cool to 20 degrees. Now, the way asymptotes work is it's not actually ever going to be 20 degrees, but because it's a real life situation, we'll say that it'll go to 20 degrees and it won't go any less. So it's probably going to be 20.0000, whole bunch of zeros and then a 1. So it's never actually 20, but to round it off, we'll say that it's about 20 there. Okay, part C, how long does it take for the coffee to reach a temperature of 65 degrees? Give your answer to two decimal places. Now, straight off the back, the fact that it said two decimal places implies that we'll use our CAS calculator. So let's set up our equation and then we will solve it from there. So we want the temperature, so that's capital T, to be 65 degrees. So we'll go ahead and substitute that into our equation. Now, of course, if you have your CAS handy, this is a great time for you to write it in and to try it out yourself. So what you would do is just simply solve that equation there. So I'm just writing the calculator instructions in red. In a normal SACRA exam, you would never do that. All right, and you should get T, little t, is equal to 8.24 minutes. Okay, part D, Manoj returns to the coffee when it has reached 65 degrees and decides to reheat the coffee in a microwave. The temperature of this coffee in this heating stage is this function here. Given that the temperature of the reheated coffee cannot exceed 85 degrees, calculate the values of A and B. Okay, So, a couple of little really bits of important information. The first thing is that he returns to the coffee, and I probably should have highlighted that along the way. So if we're following our story here, it's saying how long does it take for the coffee to reach the temperature of 65 degrees? And we're saying he comes back to the coffee at 65 degrees. So the time at which that happens is 8.24. So that's the first bit of information that I've got. When T is 65, oops, that was a bit large. When capital T is 65, little t is 8.24. The next thing is this idea that it cannot exceed. Hopefully, you can recognize that it's kind of similar to this idea. If left unattended, it can't exceed. So we're talking about in the long run, over time. And so this would imply that 85 degrees is in fact the asymptote. So if the asymptote is at, well, it would be at capital T is equal to 85, then that would imply that our A, which is the asymptote part of the equation, would be 85 there. Okay, so that's our first little bit that we can find out. A is 85. Now, in order to find our B, we just need to substitute a point that we know, which of course is this there. Now, I didn't realize my pen went a little bit crazy. I need to buy a new one. My apologies. T is 65, little t is 8.24. Okay, so when capital T is 65, we know that little t is 8.24. And so this is another situation where we can just chuck this straight into our calculator and we can now solve for capital B. And you should hopefully get an answer of B is equal to negative 3.20. So that there is our second value. So we've got A is 85 because that's the asymptote, and B is negative 30.2 because that's what we solved for there. All right, now part E says sketch a graph showing the temperature of the coffee during its cooling and warming stage. So we need it for both of these stages. So the first thing I'm going to do is draw a graph. Now we only need the right-hand side of a graph because we don't have a negative time, and we're also not reaching negative temperature in this specific case. So that'll be little t, and that will be big T. Now, let's sort of take the two scenarios. The first scenario is when it cools. We know that its initial temperature was at 95 degrees. So we're going to start right up here at 95. We probably should, because it's a set of axes, have some sort of a scale. So I might go up by 20s. 100, 20, 40, 60, 80, 100. So then 95 would be something like that there. Now, what else I do know is that he leaves it until it reaches 65 degrees, and that happens at 8.24. So 65 degrees, which will be somewhere around there, and that'll be at 8.24. Now, we don't necessarily need to put anything else in the little t scale. So, I mean, there doesn't have to be a perfect kind of uh, timeline here. I might just 6, 8, 10. You don't necessarily need to put all of these numbers in, especially because we do want to make sure that we've reached the asymptote in an accurate manner later on. But anyway, so 8.24 be about there. Okay, and then then after that, we've got an asymptote at 85. So we know from that moment onwards, we will have an asymptote. Now, again, you don't need to draw the asymptote in. I will draw it just because it's going to make my life a little bit easier. So what's happening here is that we're cooling down till we reach this particular point, and then we're heating up, but we're not touching the asymptote. Now, see how my asymptote kind of veers away? It's just because of the way that my iPad is, but yeah, that's looking a little bit better. There we go. All right, so that there would be our hybrid function. I probably would want the left and right to kind of touch a little bit better, so I might try this section again. I'm being pedantic, but it's always good to be a little bit more specific. There we go. So that's what your graph should look something like. So the fact that we have cooled down and then we have heated back up and we're reaching that asymptote of 85. So even though these points aren't accurate, you might want to try and find a point, like figure out when x is or little t is 12, what is big T. That might give you a better graph, but this is just some sort of a rough sketch at this stage. All right, moving on to our next question. Example 23, a biologist conducts an experiment to determine conditions that affect the growth of bacteria. Her initial experiment finds the growth of bacteria to be modeled by this particular rule. We've got n is equal to 22 times 2 to the power of t, where n is the number of bacteria after t days. So we've got capital N number of bacteria and little t is in days. So first part A, how long will it take for the number of bacteria to reach 2816? Now, how long means I'm looking for little t, and to reach this, that there is my capital T. So I've got the information that I need there. Now I just need to simply substitute that in. All right, so putting that into the equation, we're having a particularly bad day with the pen today. N is equal to 2816. Okay, subbing that straight into the equation. So N is equal to 22 times 2 to the power of t, which is what we don't know. Now you would chuck this into your calculator. Again, my instructions are in red. I'm trusting that you all know how to solve on your calculator. And you should get t is equal to 7 days. Part B says, what will happen to the number of bacteria in the long term according to this model? Now, this is really nice because they've actually said those words in the long term, which talks about the asymptote very specifically. Remember, in the other two scenarios, we kind of had to interpret it as like, if left unattended, that means it's talking about the long term. So this is really nice. What will happen to the long-term behavior? So we kind of just need to think about what kind of an equation this is. This is 2 to the power of t. It's just an exponential, and then it's times 22. So all that's really happening is that it's just a graph, and it's just going to keep growing forever. There's no asymptote there. The asymptote would be at 0. So it is going to continue growing, and that's all we need to say. So it will continue to grow exponentially. So even though I said in the long term means it's asking about the asymptote, in this case, we're thinking about like the asymptote already happened for this particular function. So when I'm talking about an asymptote, it's more so when it approaches an asymptote. In this case, it's approaching exponential growth. So that's why it will continue to grow exponentially. Okay, part C then says the biologist changes the condition of the growth of the population of bacteria, and it's modeled by this rule here. Show that in both of our experiments, the biologists used the same initial number of bacteria. So remember that keyword of initial, that implies that little t is equal to 0. And basically, I just need to find or like show that it's in both of the experiments. So I just need to do it for both of the equations. Now, our first equation was capital N is 22 times 2 to the power of t. So let's see what that n value is when t is equal to 0. So 2 to the power of 0 is just 1. I get n is equal to 22. So let's hope that that's what we get for our second equation as well. So same idea, I'm just going to go ahead and substitute in t is equal to 0. Now that will now be 1. So we'll end up with 66 on 1 plus 2. 66. 66 on 3. 66 divided by 3 is going to be a very lovely number of 22. All right, now the second question says, what will happen to the number of bacteria in the long term? Again, so asking us about whether it's an asymptote or just what the behavior is going to look like according to her second model. Okay, so it might not be that obvious when we have a look at this graph, because remember, we're trying to figure out what does this graph look like and where is the asymptote? And we can't tell because we haven't really seen a graph like this. So we actually have to do a mathematical calculation. Now, when we think of the words in the long term in maths implies infinity. So we're talking about t is equal to infinity, and that's exactly what we're going to do here. We are going to go ahead and substitute in t is equal to infinity. Now, it seems ridiculous to sub it in because infinity is not a number. So we're just going to kind of consider, instead of thinking of infinity as a number, because it's not, we just think of it as a really, really big number. And what happens? So let's go ahead and substitute that in. So we'll have 66 on 1 plus 2 to the power of e, 0.2 times infinity. Now remember, I'm not just saying times infinity, it doesn't make sense, but think of it as times a really, 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 really big number. So 0.2 times a really big number is going to be still a big number. So even though 0.2 is going to make it smaller, times infinity, it's still infinity. So it's a really, really large number. Now, here's what's interesting though. I just want to kind of separate this little part here to understand what is happening. Now, I want you to pay attention to the fact that it's e to the power of a negative. So that just means that it's at the bottom. So that's 1 on, and remember, e to the power of 0.2 times infinity is just basically infinity. It's a huge number. So I'm just going to write 1 on a big number. Now you try this on your calculator if you like. Go 1 divided by, and then write as many 9s as you can. The result will actually be 0. Now, it's never going to be actually 0, but it'll be very, very close to it if you were to interpret it. So whenever you do 1 divided by a massive number, you actually end up approaching 0. And so that's exactly what that section of that equation is giving there. So this part actually approaches 0. I'm not going to say it is 0, but it approaches 0. So we can say it is approximately that. So if that's the case, then 2 times 0 is just going to be 0. So this whole section of the equation, this whole section is going to be 0. Finally, that means that what is left behind is 66 divided by 1, which is simply 66. So in the long term, we're going to actually approach, so n will approach 66. And the mathematical way to write that is like this. Okay, so in the long term, the number of bacteria will be approximately 66. It'll approach 66 bacteria. All right, now this concept of substituting in infinity, kind of considering what it is in the long term, is a little bit more of a higher order skill, and it's perhaps something you haven't been exposed to yet. It is something that is how we usually teach asymptotes for the first time. So you might just want to review this concept of putting something to the negative power and what happens in the long run. But just think about it in general, anything to a negative power, and it's going to be a big number, is going to end up being basically 0. Okay, moving on to the next example. Carbon-14 dating measures the amount of radioactive carbon-14 in fossils. This can be modeled by this particular relationship over here, where Q is the amount in milligrams of carbon-14 currently present in the fossil of an organism, and T is the time in years since the organism's death. Q0 is the initial amount in milligrams of carbon-14 present. So lots of important information there. Part A says a fossil shell initially, keyword, has 150 milligrams of carbon-14 present. How much carbon-14 will be present after 2,000 years? Give your answer to correct to 3 decimal places. So labeling some of our keywords, initially is T is equal to 0, and it has 150 milligrams, which means Q, which is the amount, will be 150 when T is equal to 0. Now, because they've specifically told me that Q0 is the initial amount, and we also don't know what that is, that implies that Q0 is simply 150. They've literally told me what it is initially. Now, moving on to the actual part of the question, it says how much carbon-14. So we're looking for carbon-14 will be present after 2,000 years. So that's when T is equal to 2,000. And of course, don't forget to give it to 3 decimal places. So we're just going to go ahead and substitute it in. We don't know what capital Q is. We know that Q0 is 150. And then I'm just going to write out the equation that they gave us with a lot of numbers. And we are multiplying that by 2,000. Now, when you type that straight into your calculator, you will get 117.053 milligrams. Part B then says find the number of years, so that's little t, it will take for the carbon-14 in the shell to be halved. Give your answer correct to the nearest year. All right, very interesting. So again, let's go ahead and label. So little t is what we don't know. How to be halved. So remember Q0 was 150. That means we want Q to be simply half of that, which is 75. So this is just going to be a simple substitution. So Q0, a Q, capital Q is 75. 150 times e to the power of the very long number. T is what I don't know. And this is just a simple solve on your CAS. So type that in and you will hopefully get 5589.9. However, it does say answer correct to the nearest here. So that would apply 5590. Yes. Part C then says, suppose the amount of carbon-14 in the shell is QO on N. Find the equation relating N to T. Hence, find how long it will take before the amount of carbon-14 in the fossil shell is QO on 10. Give your answer to the nearest year. Okay, so little bit of a different kind of questions, I suppose, as to how it's worded. So let's try to break down what we've highlighted and then we can go from there. Now, it says, suppose the amount of carbon-14 in the shell is QO on N. We know that the amount of carbon-14 at any one time is Q. So that value there, QO on N, actually just represents Q in this case. So we'll start off by writing out our equation like this. And what they've told us is that at any particular time, the amount of carbon-14 that we have, so Q, is QO on N. Okay, so we've now managed to get the N into the equation, which is what we want because we want a relationship between N and T. What we don't want to see is any QOs, but that's really convenient because there's a QO on both sides. So all we have to do is divide both sides by QO. That will knock that off. So we'll end up with 1 on N is equal to e to the power of negative 0.00124 t. And now all I have to do to get N to the top, I mean, technically this is correct, right? It is an equation relating N to t, but we just want to try and give it in the nicest way possible, where I'm just going to flip it up. Now, when I mean by flip it to the other side, because this is a negative, all that needs to happen is it becomes a positive because that e part is already on the bottom. So that means N will equal 0.000124 t. So we can see a very clear relationship now between N and T. Okay, so that's the first part of the question. So we'll move that to the side. Let's have a look at what the second. Then it says, hence find how long. How long is little t? It will be before the amount of carbon-14 in the fossil shell is QO on 10. So the information that we can get from this, if we relate the QO on 10 to QO on N, you can see that this is the same. That would imply that 10 is equal to N. So basically it's saying, what is T when N is 10? That's what that's trying to tell us there. So all we have to do is just substitute it into the relationship that we just found. And we just need to solve for t. So you can solve that on your calculator and you should hopefully get 18569 years. Okay, that's it for this chapter, which is very exciting. Well done on finishing chapter 5. Good luck with your test, and we'll see you for our next chapter. Take care.